kids? Hope you're having a great day. This is the last section in chapter 10, so we're going to finish it up today. Actually, we're going to do two sections in one here in this video, but it'll still be, relatively short, 15, 20 minutes here. We're going to solve exponential equations and then also log equations at the same time. So we're going to do first 10.5.1 solving exponential equations, and so what I mean by this is when a variable is in an exponent, which you can clearly see like in number 1 and 2, the variable's in the exponent. But first off, a property of exponential equations is the following: if a raised to the x power, this should be an if a raised to the x is equal to a raised to the y power, then obviously x has to equal y. Which is, I mean, like, I know that is a little bit common sense, but basically, if you can get an equation to have the same bases, a and a, then what we can do is set their exponents equal to each other, which is important for us because then a variable's not in an exponent anymore. So it's super easy if you have this, like 3 to the 2x, equals 3 to the x minus 1. Well, bingo, you set 2x equal to x minus 1, and there you have it. You'd have x equaling negative 1 here, and we'd be good to go. 3 to the negative 2 equals 3 to the negative 2. Okay, where it gets tougher is when your bases aren't already the same, but it's actually not all that tough, and so I'm going to show you how to do this with a couple of these, and then we'll move on. So if you have a 2 as one base and an 8 as another base, my question to you is, can you get this 8 to have a base of 2? And the answer is absolutely that you can. Now, you could change this 2 to having a base of 8 as well, but it's a little bit tougher to do that. Let's actually take that 8, and let's not change the value of it, right? Let's just 2 to the 3x power. Let's take that 8 and let's write it as 2 cubed. Okay, we have not changed the value of this equation one bit. We've simply written 8 as 2 cubed, which is fine, because now we'll have 2 to the 3x equals 2 to the 15th power. Remember, when we take a power to a power, we multiply. And now our bases are the same. Now we can say 3x equals 15, and therefore x equals 5. X equals 5. Yep, that's a 5. That's a very nasty 5, but there you go. Okay, same thing here. 10 to the 7x plus 1 equals 1,000 to the 3x minus 2. Bases are not the same, but you can write 1,000 as having a base of 10. And then as soon as that happens, you can say 7x plus 1 equals, okay, this times this means you have to distribute the 3 to both of those. It would be 9x minus 6. Okay, you'll get 2x equals 7, and x will equal 7 halves there. So the goal is to get the bases equal to each other. All right, I'm going to skip to number 4, 3's. Actually, no, I'm going to do number 3 because you'll have to change both bases here. 3 squared there, and 3 cubed here. So you'll see ones where you have to change both bases, and that's okay. When we go to number 4, 1/9 we can write as 2 to the what power? Or excuse me, 1/9 we can write as 3 to what power? It's 3 to the negative second. So on occasion, it's not quite as obvious to know what to change it to, but you guys will figure it out. All right. So after you change to get the bases the same, right, then it's just a matter of saying, all right, that means their exponents have to be equal to each other. All right. So that's solving when we have two bases, one on either side of the equation. Now let's evolve here. What if you had, right, 9 raised to the x, but it wasn't equal to, another base raised to a power? It was just equal to 35. And what we'll do in these scenarios is we'll actually take the logarithm of both sides, or like these directions, or what we'll do is just we'll take these equations and write them in log form. Watch this. Okay, they're in exponential form right now, but watch, if I have an exponential equation, 9 to the x equals 35, here's the first thing that you can do. You can do what I just circled, taking the log of both sides. We can take the log base 9 of 9 to the x equals the log base 9 of 35. We just did the same exact thing to both sides. We took the log base 9 of both sides. And what that does here, if you remember from a few days ago, the log base 9 of 9 raised to the x is actually just equal to x. And it's also equal to x, by the way, because you could take that x and bring it down front here when you're expanding, and then it would just be x times the log base 9 of 9. But either way, you're just going to get x there. So x equals the log base 9 of 35, which you have change of base formula that you can plug that into your calculator for. And I'm going to pause real quick to grab my calculator. Hold tight. Stop recording for a sec. Okay, I'm back. Sorry. So the log base 9 of 35 is the log of 35 over the log of 9. Log 35 divided by log 9. That's equal to 1.62. So x equals 1.62 there. Okay, now another thing you could do, so you got that, hopefully. I'm going to erase this. It's on video, so you got it down, or just rewind it and watch it again. You can basically take this equation and just rewrite it in log form, because remember, let's go back to something simple here. If 2 to the third power equals 8, that means the log base 2 of 8 equals 3. Okay, this is review for us. So if I took this, and if 9 to the x equals 35, then that means the log base 9 of 35 equals x. Well, voila, we're already at our answer. We've got x solved for. All right, we're going to plug that into our calculator, and we're going to get 1.62 just the way we did previously. Okay, so that's how we're going to solve, by taking the logarithm of each side or just writing in log form. Now, same way, number 6, let's do number 6. 6, I'm going to write this in log form right away. This means that the log base 7 of 15 equals 9x. So now I'm close to this answer. I'm going to do the log of 15 over the log of 7, change of base formula. But then I'm going to divide that by 9, right? Like the last thing we're going to do is divide by 9, divide by 9. So change of base formula, and then divide both sides by 9, and you're going to get x equals 0.154. All right. Now, number 7, erase this again. Number 7, you want to get what is being raised to this power. See how it's e raised to the negative 0.3x. Like that is, you need to get that by itself, the base raised to the power. And that's going to take some work sometimes, because you see that minus 7. You also see it's multiplied by 4. So the first thing that we're going to do is add 7. We're going to treat this thing right here as what we're trying to get by itself, or our variable. So we add 7, and 4 times e to the negative 0.3x equals 20. Then we're going to divide by 4. Again, get that 4 out of there. We're trying to get the base raised to that power by itself. So e to the negative 0.3x is equal to 5. Now we're going to rewrite forms, only it's not a log but a natural log. This means the natural log of 5 equals negative 0.3x. It's just rewriting forms. Okay, and then we are going to do that. That's just calculator work. The natural log of 5 is 1.61, blah, 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 and then divide that by negative 0.3, and you're going to get x equaling, negative 5 point, it's an equal sign, by the way, that's really messy. Bothers me, so I'm going to redo it. Sometimes my stylus likes to drag, and I don't want it to be too loud on your video, so I drag it to be a little smoother, so it's my bad. Anyway, negative 5.36. Right, so solving exponential equations. Okay, now let's move on to our next lesson in solving log equations, which is very, very similar, but I'll give you a moment to write that down. You can hit pause on the video. Solving log equations. am I doing on time? 9 minutes, not bad. Okay, so solving log equations. We also have a property of equality for log equations, and it's the following. If the log base b of x equals the log base b of y, then that means x will equal y. And and it works the other way too. That if and only if means if x equals y, then the log base b of x would equal the log base b of y. So we have a true statement here, whether we're going from left to right or from right to left. Now there's some non-negotiables here. B, x, and y have to be positive. Remember, there's nothing negative. There was an example on your homework quiz, learning check rather. The log base 3 of negative 81. What was the answer there? The answer was nothing, none of these. This is not possible. Okay, so b, x, and y have to be positive. Our base can't be 1. So what that means is that on occasion we're going to have some extraneous solutions, and I'll show you how that looks here in this. But first, let's just practice. Whoopsies. First, let's just practice some easy ones. If you just have a log base 4 equaling a log base 4, right? 2x plus 8 equaling 6x minus 12 is what you're going to be able to do. It means these two have to be equal to each other. Okay, 4x will equal 20, and x will equal 5. Okay, now let's check that. Let's make sure when we put this in here and here, we get a positive, a positive number in parentheses, which we do. We get 18 both times, so we're golden. The log base 4 of 18 equals the log base 4 of 18. Where we would see an extraneous solution is what if we had the log base 4 of x minus 3 equaling the log base 4 of, give me a sec, 2x plus 1. Okay, what you'd have here is you'd set x minus 3 equal to 2x minus 1, or plus 1 rather, and you would get x equal to negative 4. And the problem with that is you'd have a negative 7 here and a negative 7 here. And although those two things might look the same, the log base 4 of negative 7 is not even a thing. So we would have an extraneous solution. We'd solve for it. We'd go to plug it in. And if we get a negative number there and a negative number there, we'd have an extraneous. Okay? Extraneous solution. There would not be a real solution to that equation right there. All right, and we'd move on. So in number 2, same way as natural logs. If the natural log of 7x minus 4 equals the natural log of 2x plus 11, then we're allowed to just say that means 7x minus 4 has to equal 2x plus 11. Okay, 5x equals 15, x equals 3. Plug it in, and you'll notice that we have that we have positive numbers there, and we're golden. Okay, so let's move on. Like, how would this get a little bit tougher? Well, here's how it would get a bit tougher: is if we have a log on one side and then not the same log on the other. We can't just drop the logs. Okay, but notice the directions. It says solve by exponentiating each side of an equation. Check for extraneous solutions, and you can also do this, just or write in exponential form. Right, there's kind of two ways to look at solving these. So I'm going to start by doing what the directions say. Solve by what we refer to as exponentiating, and what I mean by that is, like, how would we need to strip this log away from this so we can get the 3x minus 2 by itself. Well, what we could do is we could say, all right, I'm going to raise both sides and make them a power and make 7 my base. So I have 7 raised to the log base 7 of 3x minus 2 equals 7 to the second power. Okay, and what that will do is that will eliminate the 7 and the log base 7. Those are inverses of each other, and you would just get 3x minus 2 equals 7 squared, which is 49. So 3x minus 2 equals 49. 3x equals 51 rather. And x will equal 17. And when you plug 17 in, you get a positive, you get 49 in there, and you get 2. So you're golden. This is a legit answer. Now, instead of referring to exponentiating, watch this. I'm going to clear this page. You can just write in exponential form. Remember, let's go back to something smooth and easy. If the log base 2 of 8 equals 3, that means I can rewrite this equation in exponential form. 2 cubed equals 8. Okay, so I can take this and I can write it in a different form. 7 squared equals 3x minus 2. Boom, writing it in exponential form and solving it from there. So that's the way that I really approach these, is I write them in exponential form and get that variable by itself that way. Okay, so like in number 5, I'm going to erase this ink. Like in number 5, it's a natural log, which is fine. We're taking the natural log of x plus 7. We have that natural log by itself. Let's write it in exponential form. This means that e to the 4th power equals x plus 7. Okay, and this calculator work. E to the 4th, e, where are you at, e? There you go, e to the x. E to the 4th power is 54 point blah, 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 blah. Subtract 7, and you get x equaling 47.6. Ish. Okay, and we're golden. We plug that in, and it's positive. Okay, down here, another natural log problem in number 6. Is it going to let me extend the page? Yes, no, maybe so. Whoopsies. There we go. Extend page. So our job first is to get that natural log by itself, and we know it's just the natural log at x. There's not a parentheses around that x minus 7. It's only x that we're taking the natural log of. So first add 7, and 2 times the natural log of x equals 2. Then divide by 2, the natural log of x equals 1. And then exponentiate both sides, or just write it in exponential form. This means e to the 1st power equals x. And so x, your answer is just e here, or 2.7. I mean, e to the 1st power is 2.718, blah, 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 blah. So, I mean, you can honestly just circle that x is equal to e here. Okay, and in number 7, look at number 7. There's actually two log functions that are two log expressions that are on the same side, and it's a plus sign. Now let's go back to last section. What were we allowed to do when we were condensing into 1? When we see that plus sign, that's product rule. We would be allowed to say that that's equal to the log base 3 of x times x plus 8. Okay, which is super, super important, because watch this. That's the log base 3 of x squared plus 8x. And now we could write this in exponential form. 3 squared equals x squared plus 8x. Okay, so then that's 9, so we can subtract the 9 over and get 0 equals x squared plus 8x minus 9 equals 0. That's a factorable quadratic, x plus 9 times x minus 1. And we get answers of -9 and a +1. So there are going to be some, now it's temporary, by the way. I'm going to check both of those. But there are some, when you see two log expressions on both sides of an equation, you're going to have to condense, or on the same side, rather, of an equation, you're going to have to condense it first. And which is what I did here using my product rule from last week. And then when I have -9 and 1, watch this. Look at -9. -9 creates an issue, a big issue. -9, the log base 3 of -9 doesn't exist. So we already know -9 is an extraneous solution. Now, a +1 going there and there, all right, what's the log base 3 of 1? That's 0. Okay, 3 to the 0th power equals 1. What's the log base 3 of 9? That's 2. 0 plus 2 equals 2. That one's legit. So the only answer here is a +1. Okay, solving log equations starts with, if you have a log on either side of the equation, then go ahead and just drop the log, or and if you don't, then you're going to have to either exponentiate, or write in exponential form, or you might have to condense first. You might also have to get the same the same log expressions on one side of an equation and then condense, right? Those are some challenging ones towards the end of your homework, but by and large, this should give you a good idea of how to solve log equations and also solve exponential equations. How long did I go here? 20 minutes. All right, peace. Have a great day. Love you guys.